We're going to introduce the idea of free energy profiles for reactions. This is a follow-up of the lab you did where you determined the effective temperature on the rate of reaction. That was the iodine clock reaction. You put the test tubes in a cold water bath with ice water, and then you put the test tubes in a hot water or warm water bath at 30 to 40 degrees, and then you did the same experiment at room temperature, and you determined the effect. This is the lab. This is the reaction that you performed with the iodate and the bisulfite. And then the iodine that forms reacts with starch to turn the contents blue. And we know that that only happens at the end of the reaction when all of the limiting reactant, which is the bisulfite, has been consumed. So based on the data, you should be able to determine the rate of the reaction. And from the rate of the reaction, and you know the rate law, which you determined in the previous lab experiment that used this same reaction, you determined that this reaction was first order in iodate and first order in bisulfite, which is why you see the rate law there. Rate equals K times iodate to the first power times the concentration of bisulfite ion to the first power. So first order in both. These are the data that I collected. These will not be the same exact data that you have, but hopefully yours will follow the same trend. So you can see that temperature in degrees Celsius is in the first column. The second column is the time for the reaction to take place. From that time, we could calculate the rate of reaction, and then using the rate law and the rate and the concentrations, I could calculate the K value. So the two pieces of raw data are these two, and then these K values came from the calculation that I did using these numbers. Now, one thing that you should note is that as the temperature goes from cold to room temperature to warm, you can see that the time required, the middle column, goes down. So the reaction is faster at high temperature. We're going to talk about that. And that directly relates to the fact that the rate constant, K, is going up. And so as the temperature goes up, the rate constant goes up. And that is the first thing that we need to talk about. This is a graph from your book that shows rate constant along y as a function of temperature along x. And you can see that the rate constant, K, is exponentially related to the temperature. So as the temperature goes up, the rate constant goes dramatically up in an exponential fashion. So we're going to talk about that a little bit. And before we talk about the relationship between, the mathematical relationship between K and T, that's known as the Arrhenius equation. We will talk about that. I wanted to first talk about conceptually why that happens. And so when you think about a reaction, when we talk about free energy profile, the first thing I want to talk about is energy barriers. And so this is a picture from the textbook where you have a woman and she's trying to hit a golf ball and it needs to go over that hill in order to get into the hole. And so this is very analogous to a chemical reaction where energy is on the vertical scale, and then where she is now are the reactants. It needs to, and then the whole, of course, are the products. And in a similar fashion, chemical reactions involve a high energy hill like you see here. So the free energy profile that I'm going to show you is very analogous to this golf course image. So that's the next thing that we're going to talk about, is we're going to draw a free energy profile for a reaction. So we're going to draw on here the reactants and the products. In this case, I've drawn the products with lower free energy. We'll do an example of one where that has higher free energy later. But the important part of our free energy profile is that we have a hill that we have to overcome. The reactants have to travel through a high energy state called the transition state in order to get to the product side. This double dagger symbol that you see here is a common symbol used for the transition state. The transition state is always the highest energy state along the reaction coordinate, and it's also known as the activated complex. You see that word sometimes, but transition state's more common. I'm going to put some dashed lines here so that we can show different areas. In this case, the energy of activation, E sub A, is the energy required in order for the reaction to proceed. and that is drawn from the react. So the activation energy, or EA, is the energy required to allow the reaction to proceed. That is the energy difference between the reactants and the transition state. And that's what those words say here, right, about activation energy. And we just said this too, difference between the reactants and the transition state. Now in green here you see delta G. In this case delta G is going to be negative because our reactants have higher energy than the products, and that means our reaction will be spontaneous. We can draw a non-spontaneous reaction the same way. So we have reactants and they are lower energy, which means we have to add energy to get to products. We still have an activated complex or transition state, however, so you still need the Hill. And in this case, our energy of activation is this green arrow here, the difference between the reactants and the transition state. Remember, it's always the height of the hill that you have to overcome. In this case, delta G is positive. This is a non-spontaneous reaction. We would call it endergonic. It corresponds to the endothermic, but for delta G. But the important part is that it is non-spontaneous. And I'm labeling my transition state at the top there like I did before. So when we look at this picture from your book of a free energy profile with potential energy on the y-axis, sometimes you see that as Gibbs free energy. That's probably more common, and that is usually what I will give. And then the x-axis is either going to be reaction progress or it might be reaction coordinate. Those are both the same thing. It's not time, it's just how far along the reaction has proceeded. So on the left you see reactants, and this is just a fake cartoon reaction where we have an atom of A and it is colliding with a molecule of BC, and you know it's colliding because the picture above the graph you can see the little faded color lines indicating that they're moving together, right? They're going to collide. And then the transition state in the middle is a high energy state. And so the way you should sort of envision the transition state is that it's just kind of a strained state. It's a state where the bonds are not the ideal distance or the ideal bond angle. They're in some way strained to the point that they have very high energy, which means they're very short-lived and they're very unstable. And so it doesn't really matter if you can envision what the transition state looks like at this point. When you take organic chemistry, you'll talk a little bit about what transition states might look like in various places for certain reactions. Just remember it's high energy, okay? And then the products on the right-hand side of our fake reaction are a molecule of AB and then an atom of C. And so you can see the energy of activation is the green arrow. That's the distance between the reactants and the transition state. It's the energy that has to be put into the reaction in order to get it to proceed forward. Delta E, or might be called delta G, is the thermodynamic change in energy for the reaction. And so in this case, the products have less energy than the reactants. And so this would be a spontaneous or exergonic reaction. We'll talk more about that. Now, just as a reminder, you'll see in the same in another video on collision theory the effect of temperature on the rate of reaction, and that's shown in this graph here. This is the second time you'll see this graph, or the first of two times you might see this graph. So temperature is a measure of kinetic energy, and if you notice, the blue graph is sort of a normal temperature, and then if you increase the temperature, that changes the number, the sort of profile of how many collisions have a certain amount of energy to the purple graph, and so it shifts it over. And what happens is that the purple shaded region on the right, those are all of the molecules that have at least the activation energy. So the activation energy is the minimum energy needed for the reaction to occur. And you can see the purple shaded area is much larger than the blue shaded area, which is why more molecules react appropriately to product at higher temperature. The last thing I want to talk about is the effect that catalysts have on the free energy profile. So if we draw a free energy profile with reactants and products and the transition state, which is the highest energy state, this would be a typical uncatalyzed reaction, the same energy profiles we've been talking about. The effect that a catalyst has is it lowers the free energy of the transition state. It gives an alternative path for the reaction coordinate. So you can see the catalyzed reaction, there's no red line here, but it's just because it's overlapping with the black line. The free energy of the reactants is unchanged by a catalyst. The free energy of the products is unchanged by a catalyst, but the free energy of the transition state is lowered. And so this is what it means by giving an alternative path. Now it has a lower path to get from reactants to products, and that's why it enhances the rate, because the hill is lower now. So it lowers the activation energy. And so I'm going to put in here the catalyzed reaction is shown in red. And if we draw a new activation energy, then that is the arrow, the orange arrow now from the reactants to the new transition state. And so this is a lower activation energy, which is why the rate is higher when the catalyst is present. So let's define a catalyst. A catalyst is a substance that increases the rate of the reaction by lowering the free energy of the transition state. It is not consumed in the reaction, which means it is not a reactant. So you don't draw it on the reactant side, because reactants are by definition converted into product. And so reactants go away and products are formed. Catalysts are neither created nor formed during the reaction. They are not consumed. So they're present at the beginning and they're also present at the end. What we'll see when we talk about mechanisms is that some catalysts are converted in an intermediate step to an intermediate, but then they are reconverted back to themselves by the end. And so we'll see that a catalyst may participate in the reaction, but it's reformed by the end. And so when you look at the overall reaction, it looks like nothing has happened and it's just sitting there. And so catalysts are always written on the arrow itself to indicate that they are neither reactants nor products. So they are therefore written on the reaction arrow, just like any other thing that is required for the reaction to proceed, like heat or high pressure or whatever else you need for a reaction to proceed. You write it on the line, and therefore you write the catalyst on the line as well. Here we're going to do some free energy profile practice. Consider the following free energy profile for a hypothetical reaction. Label the transition state on the above graph. So I zoomed in here. I don't really know if that was necessary, but the transition state is the highest energy state, so it's at the top of the hill. So that's here. The double dagger symbol is the abbreviation for transition state. So the state right here at the very top, right there at the top, is the transition state. Part B, estimate the value of the activation energy for this reaction to the nearest kilojoule per mole. So the activation energy is the distance between the reactants and the transition state. And so if you think about your axis here, if we add in numbers that aren't shown, then the activation energy is approximately 175, which is where the transition state is, minus 25, right? So that's about 150 kilojoules per mole. Estimate from the graph the value of the activation energy for the reverse reaction to the nearest 10 kilojoules per mole. The reverse reaction is going to start with the products and then go up to the same transition state that has that in common. And so in that case, we have 175, which is our transition state, minus our products, which are at about 110 or so kilojoules per mole. So the activation energy of the reverse reaction is 65 kilojoules per mole, approximately. Estimate the change in free energy for the reaction to the nearest 10 kilojoules per mole. So that's going to be the distance between products and reactants. The products have a higher free energy, which means this value is going to be positive, right? Energy must go in. So we have about 110 minus about 25, which gives us about 85 kilojoules per mole. It's positive, which means it is spontaneous or endergonic. And that's because the products are greater than the reactant free energy and because delta G is positive. For both of those reasons, you know that answer. We're going to draw the effect a catalyst would have. We're going to do that in F. Part F, I'm going to erase some of the stuff so you can see it more clearly. So we're going to do it in red on top of it. The catalyst does not change the free energy of the reactants or the products, but it lowers the free energy of the transition state, which has the effect of lowering the activation energy, right? Which is why it increases the speed of a reaction. The next set of practice problems consider these activation energies in delta G's provided below. Sketch the free energy profiles and then determine which one is the fastest and which one is the slowest. So here, the activation energy needs to be about 45, and delta G is negative 25. If we do part B, we have a similar, slightly smaller hill, and then less of a decrease. And then part C, 55 and 10 kilojoules per mole, gives us this free energy profile. So remember the activation energies, there's always a hill between the reactants and the transition state. And then delta G is determined by the difference between the reactant line and the product line. So the spontaneous reactions with negative delta G's, for example A and B, they have products which have a lower free energy than the reactants. And for part C, or for reaction C, the products end with a higher free energy because those have a positive delta G value. The last part of this, we're supposed to determine, oh, here, I was going to add this in even though the question doesn't ask us this. The activation energy for the reverse reaction in this case would be this distance, 25, plus the 45 here. And so that would be about 70 kilojoules per mole. The activation energy for the reverse reaction would be about 45 kilojoules per mole. And for this one, it would be the difference. It would be about 45 kilojoules per mole also. Now, the second half of this question, determine which would be fastest and which would be slowest. The fastest one is going to have the lowest activation energy. The delta G value doesn't really affect at all the rate of the reaction. The rate of the reaction would be determined by EA. Now, this is assuming, and any question I give you on the quiz or on an exam would include this assumption that I should have written out here in words. You're going to assume that everything else is constant. So you're going to assume that the temperature is constant. You're going to assume that the rate law is the same and the concentrations of all reactants are the same. And you're going to assume that the pre-exponential factor, right, the frequency factor is the same. So those are all things that influence K, but the only one, between EA and delta G, the only one of those that influences K is the activation energy. And so the fastest one will have the smallest hill to get over, and the slowest one will have the largest hill to get over. So the slowest one is C and the fastest one is B. Let's do the second part. We have a friend studying first order reaction, obtains these three graphs for experiments done at two different temperatures. Which lines represent experiments done at the same temperature? So here we have a natural log of A as a function of time. So this is basically a first order reaction. We know that because this plot is linear. And so remember the slope is related to the rate constant, right? And so different temperatures are going to give you different rate constants. The same temperature is going to give you the same rate constant because it's the same reaction. Everything else is the same. So that means that we're looking at the slope. There it is right there. So the slope is negative K, and the y-intercept is the natural log of the initial concentration. So the ones done at the same temperature, T is in this equation, everything else is a constant. That means that when temperature changes, the K changes, and that changes the slope. So you're going to look for the two that have the same slope, which is 1 and 2. Those must be at the same temperature because they have the same slope or same value of K. What accounts for the difference? The difference is that they have two different y-intercepts, which means they have two different starting concentrations of reactant. In what way are they the same? We already kind of said that. They have the same slope. which means they have the same K value, which means they were done at the same temperature. Which two lines represent experiments done with the same starting concentration but at different temperatures. So those are going to have the same y-intercept, but they're going to have different slopes, right? So here, 2 and 3 have different slopes but the same y-intercept. Which one is the lower temperature? The lower temperature is going to be the one that has a lower K value, right? Because as temperature goes down and down and down, the rate goes down, and that's because the rate constant is going down. So lower K means it has a lower slope. So the lower temperature is going to be the one with the lower slope, which is 3. And how do you know? I think we just explained that. Lower T, lower K, all that. Consider a series of reactions having the given energy profiles. Rank the reactions from slowest to fastest, assuming they have nearly the same frequency factors. So here, remember that the slow reaction is going to have a big hill, large activation energy, and a fast reaction is going to have a small hill, or a small energy of activation. So slowest is the biggest hill, which appears to be 25 kilojoules per mole. And the fastest is going to have the smallest activation energy, which appears to be number 1. The slowest one is going to be number 2. Now let's talk about the reverse reactions. I know the question doesn't ask us about that, but we might as well include that. The activation energy for the reverse reaction for number 1 appears to be about 25 kilojoules per mole. For reaction 2, it appears to be about 40 kilojoules per mole if we add those two numbers together. And for the third reaction, it appears to be 20 minus 5, which is 15, right? This whole thing here, it's kind of hard to read. This whole thing is 20, and this distance here is just 5. So if you're just going from here to here, that's only 15. So in the reverse reaction, the slowest one is going to have the highest activation energy. That's still number 2. And the fastest in the reverse direction is going to be reaction 3 because it has the smallest activation energy.